Ladies and gentlemen, welcome to a short video summarizing the contents of the Fivefold Sun as a book published in 2017 and as a series of 30 video lectures. This short video was recorded in December 2018. The Sun is a spherical ball which emits light. Its kinematics are known through its rotation of about 27 days at the mid-latitudes and the variation in its emission of light, an activity cycle of about 11 years. The Sun's differential statistics are a little bit more complex. There is in fact differential rotation in the solar ball, only 25 days at the equator and about 40 days near the poles. The light variation cycle has a length which is, as a mean, about 11.1 years, but as a median, as a peak frequency, quite different, only 10.6 years. As well, the rise leg of this cycle is only 4 years, while the fall leg is 6.6 years long. So this is not a sine wave. The Sun in time displays a behavior which is as follows. Differential rotation, the angular velocity at the equator is nearly 1.6 times the angular velocity at the poles in a latitude band of plus or minus 5 degrees about either pole and about the equator. The length of the cycle, if we now express it in numbers of rigid rotations, as a mean is 150 rotations, and is the sum of 60 and 90 such rotations for the rise and the fall legs. But as a peak frequency, as a median, its length is only 144 rigid rotations, the square of 12, and is the sum of 55 and 89 such rotations for the rise and fall legs. As you can see, 144 is 89 multiplied by 1.6, etc. And again, 89 is 55 multiplied by the same factor. In space, for the differential rotation from equator to pole, and over time, a ratio of about 1.618 is found in each case. The solar kinematic in time can be expressed in generalized Fibonacci numbers. The activity cycle length can be expressed as Fibonacci numbers. The numbers as given in the previous pages, 144, 55, and 89 are Fibonacci numbers from this well-known sequence, 1, 2, 3, 5, 8, 13, etc. But also the differential rotation numbers, the numbers of rotations at the equator over a cycle is 157, at the pole 97. Their difference is 60, i.e. 60 laps of the equator versus the pole. And these are generalized Fibonacci numbers from a sequence 1, 4, 5, 9, etc. that we can call here the solar sequence. There is as well, according to results obtained separately in this work, a set of intracycle quasi-periodicities in solar activity which can be expressed in Lucas numbers, which are also generalized Fibonacci numbers. For instance, the well-known QBO, the quasi-biennial solar period of about 2.14 years, equals 29 rigid rotations. 29 is the 7th Lucas number. Same for these companion quasi-periods about the quasi-biennial central period. The Lucas numbers are 1, 3, 4, 7, 11, etc. This is a table in which the three said sequences are summarized: the main Fibonacci sequence and its two expressions, the Lucas sequence and the solar sequence. Highlighted are the numbers of rigid rotations here for the solar ball that we found in the previous pages, the numbers of rigid rotations of quasi-biennial intracycle periodicities, and the differential rotation numbers, equatorial rotations, polar rotations, and their differences. The differential rotation numbers again are those, and they are also found in the numbers of bipoles in the main sunspot groups at peak activity epoch in the solar cycle. If you count the numbers of bipoles in the largest sunspot group in terms of numbers of sunspots in it, the second largest, etc., to the fifth largest, you will find that their characteristic statistical counts are 23, 14, 9, 5, 4, and these are the consecutive integers here in the solar sequence, which are preceding those that we mentioned before, which are accumulated over the solar cycle in terms of field winding laps. So in total, we have at the peak epoch of a full cycle 60 accumulated field line laps corresponding in each hemisphere of the Sun, north or south, to 60 bipoles as a characteristic number at the surface of the Sun. Also, in the longer term, the same series of generalized Fibonacci numbers is found in long-term solar oscillations. The 16th solar sequence number is this total, and in rigid rotations corresponds to 207.7 years, which is within error bars identical with the well-known Suze-de Vries cycle in solar activity. As well, the 21st one corresponds to this number, and in rigid rotations is 2,303 years, which is extremely close to the length of about 2,300 years, estimated for the so-called Hallstatt cycle of solar oscillations. The key to this numerical kinematic is this ratio, which we already mentioned, to which tend a ratio of two consecutive Fibonacci or generalized Fibonacci numbers, and is defined by this mathematical expression. This ratio is found in the sides of the pentagon and is found in fivefold regular solids. For this reason, we will now look into the possibility of a fivefold symmetry in space in the Sun. First, in the Sun's volume. Fivefold symmetry in the volume of the solar ball is found in observations from the radius of the energy-generating core, about 0.31 of the photospheric radius, which corresponds to an icosahedral radius, and the radius of the envelope of rigid rotation, 0.65, perhaps 0.655 of the solar radius, which would exactly match a radius defined in an icosahedron concentric with the solar ball, in which 12 equal spherical balls would be tangential to the central core. This would represent a realization of the very well-known icosahedral spherical code. We now show a 3D model of the suggested such arrangement with 12 balls. This is the suggested arrangement. The glass envelope is supposed to represent a circumscribing sphere. In the case of the Sun, it would be the photosphere. And you see balls of equal diameter. There are 12 of them. The top one is in a polar position along a rotation axis, the bottom one as well. And if we take away a polar ball, we can see that the 12 balls are tangential to a imaginary core, which would, in the case of the Sun, correspond within error bars to the size of the energy generating core. This is a 2D projection of this arrangement in perspective. Only 4 of the circles that you see are in the same plane, in the plane of the sheet. The dotted circle here is the circle representing the inner core, to which are tangential the 12 outer spheres. And the orange dotted circle is a circle and a sphere passing through the centers of each of the 12 outer balls. The radius of this circle is 0.655 times the radius of the circumscribing sphere by construction, and the radius of this core is by construction 0.31, etc. This is now a cartoon showing how this arrangement explains the presence of a corridor from the outer envelope of the rigid rotation zone in the Sun to the solar surface, which reaches the surface at a latitude of 38 degrees. And this is, by construction, obtained in the icosahedral arrangement. We now investigate the possibility of fivefold symmetry also at the solar surface. It is found in the distribution of sunspots and activity centers. Indeed, the peak density of sunspots is found at 11 degrees, and 10.8 degrees is the latitude of the center of a toroidal icosahedral face in the suggested concentric icosahedron for the Sun. As well, the well-known active longitudes in solar activity seem to cluster at the central longitude of each of 5 alternate toroidal faces in each north or south hemisphere of the Sun. These results are found in the research performed during the Fivefold Sun project. It consists of 6 parts. You see the names of each parts. 3 are geometrical in nature, 3 are numerical in nature. These are the contents of these parts in the book, in the text and electronic version of the book. And the project consists as well of 30 video lectures. You can look at the so-called video 0 for the contents of the video lectures. It is called the Fivefold Sun Video 0, and the other videos are numbered from 1 to 30. There are in text 15 paper volumes covering 15 years of research. My name is Jean-Guillaume RICHARD. I am the author, and I thank you for your attention and interest.